All right, let's unpack this deep dive into the world of q-Painlevé equations. You've sent over some fascinating research on a particular type, A17, and its connection to something called the Kyiv formula. I have to admit, even for someone who loves math, this stuff is pretty dense. But that's why we have our expert here to guide us.
It's definitely an area that's seen a lot of exciting progress recently. For a long time, finding general solutions to these q-Painlevé equations was considered incredibly difficult. The Q formula is a major breakthrough because it allows us to represent those solutions as explicit combinatorial series, which opens up a whole new world of possibilities for understanding them.
Okay, so before we get lost in the weeds, can you give us a quick refresher on what makes q-Painlevé equations special? I know they're related to differential equations somehow, but it's all a bit hazy for me.
Absolutely. So you're probably familiar with differential equations, which describe how things change continuously over time. Well, q-difference equations are like their discrete cousins. They deal with changes over discrete steps, kind of like a sequence of snapshots instead of a smooth movie.
Ah, okay. I'm starting to see the picture. And I remember hearing something about a Painlevé property that's important here.
Exactly. In the world of differential equations, Painlevé equations are special because their solutions have a unique property concerning their singularities. Those points where the solutions can become infinite or blow up. In Painlevé equations, these singularities can only be poles, which are relatively tame compared to the wild singularities you can get in other differential equations. This Painlevé property is closely related to the idea of integrability for systems that change over time.
So it's like these Painlevé equations have a built-in safety mechanism that prevents their solutions from going completely haywire, even at those tricky singularity points.
That's a great way to think about it. Now, in the realm of q-difference equations, this Painlevé property is replaced by something called singularity confinement. It basically means that if a solution becomes infinite at some point during its discrete evolution, it will always return to a finite value within a finite number of steps. It's like a mathematical boomerang. It might fly off towards infinity for a bit, but it always comes back.
I love that analogy. So this singularity confinement property is what makes q-Painlevé equations special in the discrete world.
Precisely. Now, the specific q-Painlevé equation we're focusing on today, type A17, can be written as G2T, GT2 plus GT2 plus 1. This equation might seem a bit intimidating at first glance, but what's fascinating is that it arises naturally from a condition called a compatibility condition.
Okay, compatibility condition. That sounds intriguing. Can you elaborate on that?
Sure. To understand the compatibility condition, we need to introduce a matrix function, y_is. This function depends on two variables, t and z, and it evolves according to two different equations labeled as 2.1 and 2.2 in the research you've provided. These equations describe how y_d changes as we adjust the variables t and z.
So we have this matrix function dancing around according to these two equations. Where does the compatibility come in?
The magic happens when we require that applying either equation 2.1 or 2.2 first leads to the same end result for y_. This requirement, ensuring the evolution of y_, is consistent regardless of the order of operations, is the compatibility condition. And it's this condition that gives rise to the q-Painlevé equation we're studying.
So it's like we have two different paths to get to the same destination, and the compatibility condition ensures that those paths don't lead us astray.
Exactly. And it's remarkable that this seemingly simple requirement leads to such a rich and complex equation like the q-Painlevé A17 equation.
Now, you mentioned these equations involve some special matrices. I see equations 2.3 and 2.4 in the research, defining matrices LTZ and beta. What's the story with those?
Ah, yes. These matrices are crucial. They are constructed using the function gt, which is the very function that appears in our q-Painlevé equation. This connection hints at a deep relationship between the seemingly simple linear system, described by equations 2.1 and 2.2, and the nonlinear q-Painlevé equation itself.
That is fascinating. It's like these matrices are acting as a bridge between the linear and nonlinear worlds. So we have this compatibility condition, this matrix function, and these special matrices. Where do we go from here?
Well, a key tool in studying q-Painlevé equations is something called the Becklin transformation. It's a remarkable technique that allows us to generate new solutions from existing ones.
Okay, that sounds like something out of a mathematical magician's hat. How does this transformation work?
In the context of the q-Painlevé A17 equation, the Becklin transformation relates the function gt to a new function, g tilde of t, through the relation g tilde of t equals the square root of t divided by gt. This is equation 2.12 in the research.
So if we know one solution, gt, we can plug it into this formula and poof, we have a brand new solution, g tilde of t.
Exactly. It's a powerful tool for exploring the solution space of the q-Painlevé equation, and what's even more fascinating is how this transformation affects the matrix function, YIOT.
I'm all ears. How does the Becklin transformation play with YAT?
Well, applying the transformation leads to a transformed function denoted as y tilde of ez. This is given by equation 2.9 in the research. And what's remarkable is that the equation defining y tilde of itz closely resembles that of the original ytz, but with gt replaced by our new friend g tilde of t, it's like the transformation creates a parallel universe where the solution evolves according to similar rules, but with a slightly twisted function.
Okay, I'm starting to see how this Becklin transformation adds another layer of complexity and intrigue to the whole picture. But before we dive deeper into that, can we talk about this concept of monodromy? I know it has something to do with how solutions behave around singularities, but I need a little more clarity.
You're right on track. Imagine tracing the path of a solution as it winds its way around a singularity in the complex plane. Monodromy captures how that solution changes when you complete a full loop around the singularity. It's like taking a mathematical journey around a strange object and observing how the landscape transforms along the way.
So it's like a way to measure the twist that the solution undergoes as it navigates those tricky singular points.
Precisely. Now, in the context of the q-difference linear system associated with q-Painlevé A17, this monodromy is elegantly represented by a matrix called the monodromy matrix, often denoted as M. This matrix relates the values of a solution y(RZs) at different points that are related by a loop around a singularity. It's like having a mathematical decoder ring that allows us to decipher how the solution transforms as it circles the singularity.
I'm starting to feel like a mathematical explorer charting unknown territory. So we have this monodromy matrix that captures the twist. What can we do with it?
Well, one of the key things we can look at is the determinant of this matrix. Remember from linear algebra that the determinant tells us something about the volume scaling of a matrix transformation. In this case, the determinant of y(-) is remarkably well behaved. It's analytic, meaning it's smooth and predictable, invertible, which means it can be undone, and most importantly, it's single-valued within a specific region of the complex plane. This is all captured in equation 2.17.
Okay, so the determinant of y(-) is playing nice. But what about the determinant of our monodromy matrix M?
That's where things get really interesting. The single-valued nature of the determinant of y at z actually implies that the determinant of M is equal to 1. This might seem like a small detail, but it has profound implications.
I'm sensing a but coming.
You're right. Remember from linear algebra that a determinant of 1 means that the matrix can be diagonalized. This means we can express it in a simpler form where all the off-diagonal elements are 0. This is given by equation 2.22. This diagonalization allows us to represent the matrix in terms of a single parameter denoted as sigma as shown in equation 2.24.
So it's like we've distilled the essence of the monodromy matrix into this single parameter, sigma.
Exactly. And here's the beauty of it. We can now express the solution, y at z, in a form that explicitly highlights its monodromy properties. This is equation 2.25.
So we've tamed the wild monodromy beast and captured its essence in this elegant equation.
In a way, yes. But there's a catch. The monodromy parameter, sigma, only tells us part of the story. To fully understand the behavior of the solution, we need to investigate how it acts near 0 and infinity. This is where the concept of parametrices comes into play.
Parametrices, they sound like something out of a science fiction novel. What are they and why do we need them?
Think of parametrices as clever approximations to the full solution, y at z, specifically near those troublesome singular points at 0 and infinity. It's like zooming in on those points with a mathematical microscope to see what's really going on.
Okay, so we need these parametrices to get a close-up view of the solution near the singularities. How do we find them?
They are obtained by solving simplified regions of the original q-difference linear system. These simplified equations are given by 3.1 and 3.2 in the research. Their solutions involve special functions called q-Bessel functions, as shown in equations 3.3 and 3.4. These q-Bessel functions are essential for understanding the intricate behavior of the solution while you're in the singularities.
Q-Bessel functions. Another new character enters the stage. I'm guessing these functions have some special properties that make them suitable for this task.
You're absolutely right. They have a rich mathematical structure and are well studied, which makes them valuable tools in this context. Now, the solutions to these simplified systems come with their own set of parameters, 0 and infinity, which are associated with the behavior of the solution near 0 and infinity, respectively. And here's a key insight. These parameters, alongside our monodromy parameter, sigma, capture the complete monodromy data of the Q-difference system. It's like we've assembled a mathematical fingerprint that uniquely identifies the solution's behavior around the singularities.
So Vero 0, Sinfinity, and sigma, our monodromy dream team. What do we do with this complete monodromy data?
A key result, summarized in Theorem 3.1 and visualized in Figure 1, states that the ratios of the parametrices to the full solution yTCZ are analytic and invertible inside and outside a specific circle in the complex plane. These ratios are represented by the functions capital Phi plus of and capital Phi minus of TZ. This result is crucial because it allows us to construct something called a Riemann Hilbert problem, which provides a powerful framework for studying the q-Painlevé equation.
Riemann Hilbert problem. That sounds intimidating. Can you give us a glimpse into what it's all about?
Imagine you have a function defined on a complex plane that needs to satisfy certain conditions or jumps as you cross specific boundaries. The Riemann Hilbert problem is essentially about finding such a function given these jump conditions. It's a bit like solving a mathematical jigsaw puzzle where the pieces are functions and the boundaries define how they fit together.
So we're using this Riemann Hilbert problem as a new lens to examine the q-Painlevé equation.
Precisely. And to add another layer of complexity, Lemma 3.2 reveals that our parameters, 0 and infinity, are actually periodic functions of the time variable t. It's like they're dancing to the rhythm of time.
Okay, so our monodromy data is not static. It evolves over time. This is getting pretty wild. Where do we even go from here?
Well, now that we have a good grasp of the monodromy properties of the solution and its behavior near singularities, we can delve into the concept of the tau function, which is intimately connected to the q-Painlevé equation. To define this tau function, we'll need to explore the world of determinants, which are powerful mathematical tools for capturing important properties of matrices.
Determinants, I remember them from linear algebra. They tell us something about how a matrix scales volumes, right?
Exactly. But we'll be using a more specialized type of determinant called the Wyndham determinant. It's a way to compute determinants of certain types of operators, which are like generalized functions that act on other functions. And this Wyndham determinant is crucial for defining the tau function denoted by tau of t associated with the q-Painlevé equation.
So this tau function is built from determinants and is somehow related to the q-Painlevé equation. I'm eager to hear more about its significance.
Welcome back. It's amazing to see how these different branches of mathematics weave together, isn't it? Last time, we left off talking about the tau function and its connection to Nekrasov functions from theoretical physics. Now, let's explore some alternative ways to represent these tau functions.
Alternative representations. It's like having different maps to navigate the same mathematical terrain. What's the advantage of having multiple representations?
Each representation offers a unique perspective and can be advantageous for different purposes. Some representations might simplify calculations, while others might reveal hidden symmetries or connections. Remember, we initially expressed the tau function using a specific factorization of the jump matrix denoted as J02. This factorization involved solutions to auxiliary linear systems, represented by Psi2 and Sissi+.
Okay, I'm vaguely remembering that from our last discussion. And this factorization led us to a specific tau function, right?
Yes, it led to the tau function we denoted as tau, which can also be expressed as tau2 equals det, I is 0.d2. These are equations 6.4 in the research.
Right, those equations are starting to look familiar. And those A0, D2 are operators, if I recall correctly. They're like mathematical machines that act on functions.
Precisely. And their kernels, which determine how they act on functions, are given by explicit expressions involving q-Bessel functions. You can find those expressions in equations 5.4 and 5.17. However, there's a subtle but crucial detail here. The q-Bessel functions appearing in these expressions have different indices, J0 and J2. Those indices, 0 and 2, are directly related to the superscripts in our notation for the tau function tau2.
So the indices of the q-Bessel functions are encoded in the tau function's notation. Interesting. What happens if we change those indices?
That's the exciting part. It turns out we can generalize this concept and consider tau functions with other superscripts. These correspond to alternative factorizations of the jump matrix, involving different q-Bessel functions. It's like we're exploring a whole family of tau functions, each with its unique set of indices and q-Bessel functions.
Okay, I'm starting to see how this works. So by changing the indices of the q-Bessel functions, we're essentially creating new tau functions.
Exactly. For instance, we can introduce matrices psi-r and psi-1a as defined in equations 6.7 and 6.8. These matrices are solutions to alternative linear systems given by equation 6.9, with coefficient matrices LK0 defined in equations 6.1, 6.11, and 6.12. These alternative linear systems lead to tau functions denoted as tau k equals det ia0 dk.
So we're basically swapping out the q-Bessel functions and seeing how it affects the tau function. What kind of insights do we gain from this?
Well, a key observation captured by equation 6.17 is that modifying both the A and D operators in this way results in a shift in the tau function's superscript. Specifically, we have toc1 k2 equals toc1 k2. This allows us to explore tau functions with indices k ranging from -2 to 2. It's like we're creating a whole spectrum of tau functions.
A spectrum of tau functions. I
Yeah.
love that image. But why do we care about these different representations?
Different representations can be more convenient for different purposes. For example, certain representations might simplify calculations or offer insights into the tau function's properties. A particularly interesting case is the relation between the tau functions with k, or 0, and k equals -2. This relation is governed by a generalized Séguin formula, given by equation 6.23.
The Séguin formula, it sounds familiar from complex analysis.
You're right. The Séguin formula, in its various forms, appears in many areas of mathematics. In this context, it elegantly captures how the determinant changes when we modify the jump matrix by a scalar factor.
A scalar factor, so we're just multiplying the whole matrix by a simple number.
Exactly. And in this specific case, the scalar factor is given by Ct2, which relates the matrices sine and C2 as shown in equation 6.25. By carefully applying the generalized Séguin formula and using some properties of q-Pochhammer symbols, we can derive the prefactor, qtqqq, which elegantly connects the tau functions tau and tau2. This result is summarized in equation 6.28.
So we're essentially connecting different tau functions through this scalar factor in the Séguin formula. It's like finding hidden bridges between different parts of our mathematical landscape.
Precisely. And remember those renormalized tau functions denoted as tk that we introduced in equation 5.70? They're closely related to these tau functions we've been discussing. In fact, theorem 6.1 establishes a precise relationship between t0 and t2.
Okay, so we have a whole web of interconnected tau functions. But how does all this help us understand the q-Painlevé equation itself?
Well, remember those parameters 0 and infinity that we introduced earlier to describe the behavior of solutions near 0 and infinity? They play a crucial role in connecting the local asymptotics of solutions to the tau functions.
Asymptotics, that's about how functions behave as their arguments get very large or very small, right? It's like looking at the behavior of the solutions at the edges of our mathematical universe.
Exactly. We define vectors capital omega of t and capital omega of 1 in equation 7.1. These vectors capture the behavior of solutions near the singular points zr and zq, respectively.
And you mentioned a connection between these vectors and the tau functions.
Yes, by carefully analyzing their evolution equations, as shown in equations 7.2 and 7.3, we discover that certain ratios of their components remain invariant under the isomonodromic evolution.
Isomonodromic evolution. Can we pause for a second? What does isomonodromic even mean in this context?
Of course. Isomonodromic essentially means having the same monodromy. Remember, monodromy describe how solutions change as they circle around singularities. So, isomonodromic evolution refers to a process where the monodromy properties of the solutions are preserved, even as the parameters of the system change.
Okay, that makes sense. So these certain ratios of the components of those vectors stay the same, even as things change over time, as long as the monodromy remains constant.
Exactly. And these invariant ratios can be expressed explicitly in terms of those parameters, L0 and infinity. This connection is revealed in equations 7.4 and 7.16.
Wow, so those seemingly abstract parameters are directly linked to the behavior of solutions near singularities. I'm starting to appreciate how elegantly everything fits together.
It is quite remarkable. Now, we can use these local asymptotics to explore how the q-Painlevé transcendent, GT, transforms under a specific change of variables. It goes to open t. This transformation is like flipping our mathematical landscape, and we're curious to see how it affects the solution.
It's like looking at the equation through a mirror.
Precisely. And by carefully analyzing how the linear system and its solutions behave under this transformation, we uncover a fascinating relationship captured by equation 7.57. This equation links the original q-Painlevé transcendent GT to its transformed counterpart, G1a, through those parameters 0 and infinity.
Okay, so we're seeing how the solution changes when we flip our perspective. But what about the tau function? How does it behave under this transformation?
We can also express the transformed tau function, tau1t, in terms of the original tau function and those parameters, 0 and infinity. This relationship is summarized in equation 7.88.
It's amazing how those parameters keep showing up everywhere. They're like the hidden threads that connect the entire mathematical tapestry.
They are indeed, and these connections go even deeper. We can also use these techniques to derive something called fusion kernels.
Fusion kernels. Those sound like they come from a science fiction movie.
They might sound futuristic, but they're rooted in the mathematical world of conformal field theory. These kernels describe how special functions called conformal blocks combine and interact. And using the insights we've gained from studying the q-Painlevé equation, we can derive explicit expressions for these fusion kernels. Equations 7.9 and 7.94 provide examples for specific cases related to conformal blocks with central charges C and C equals 1.
Okay, so we've gone from q-Painlevé equations to tau functions to local asymptotics to transformation properties, and now to conformal field theory. My head is spinning with all these connections.
It has been quite a journey. We've covered a lot of ground in this deep dive, but there's still more to explore. In the final part, we'll wrap things up by discussing some open questions and potential directions for future research. Stay tuned.
Welcome back for the final part of our deep dive into q-Painlevé equations. We've been on quite a mathematical roller coaster ride, haven't we? From monodromy matrices to tau functions to fusion kernels, it's amazing to see how all these pieces fit together. But I know this is an area of active research, so I'm guessing there are still plenty of unanswered questions and uncharted territories.
You're absolutely right. The research you've shared with us represents significant progress in understanding q-Painlevé equations, but there's still so much more to explore. It's like we've mapped out a small portion of a vast mathematical continent.
Okay, so what are some of the big open questions that mathematicians are grappling with in this area? What are the frontiers of research in q-Painlevé equations?
Well, one avenue of research is to generalize these techniques to other q-Painlevé problems. Remember, we've been focusing on a specific type of q-Painlevé equation, type A17, but there's a whole universe of q-Painlevé equations out there, each with its own set of complexities and challenges.
So it's like we've climbed one mountain, but there's a whole mountain range waiting to be explored.
Exactly. And there are also intriguing connections to explore with other mathematical objects, like the Aronkin-Borodin tau functions. These tau functions arise in the study of certain integral systems, and there are hints that they might be related to the tau functions we've been studying in the context of q-Painlevé equations.
That's fascinating. It's like discovering hidden tunnels connecting seemingly different mathematical caves.
Indeed. Another interesting direction is to explore how these techniques might be applied to study Riemann Hilbert problems on more complex geometric objects, like a torus, which is a donut-shaped surface. Remember, we discussed how the Riemann Hilbert problem allows us to study functions with certain jump conditions across boundaries. Extending these ideas to more complicated geometries could lead to new insights and applications.
So we're talking about taking the tools we've developed and applying them to even more challenging mathematical terrains.
Yeah.
What about those free fermionic constructions of vertex operators that you mentioned earlier? I have to admit that went a bit over my head.
Those are definitely more advanced topics, but they hint at some deep connections between q-Painlevé equations and conformal field theory. Vertex operators are powerful tools in conformal field theory, and there are indications that they might offer new perspectives on the q-Painlevé equations. Exploring these connections could lead to new insights and breakthroughs.
Conformal field theory is a whole other area of mathematics that I'm only vaguely familiar with. Could you give us a quick overview of how it relates to q-Painlevé equations?
Conformal field theory is a branch of mathematical physics that studies quantum field theories with a special kind of symmetry called conformal symmetry. The symmetry essentially means that the theory is invariant under transformations that preserve angles. Now it turns out that some of the mathematical structures that appear in conformal field theory, like vertex operators and conformal blocks, have intriguing connections to the tau functions and other objects we've been studying in the context of q-Painlevé equations. It's like we're finding a common language between these seemingly different areas of mathematics.
That's pretty mind-blowing. So we have connections to integral systems, Riemann Hilbert problems on different geometries, conformal field theory. It seems like the possibilities are endless.
They really are. And let's not forget about those connections to q-difference spectral problems that we touched upon earlier. These problems involve studying the eigenvalues and eigenfunctions of certain q-difference operators, which are like the discrete counterparts of differential operators. There are intriguing connections between these q-difference spectral problems and the q-Painlevé equations, suggesting that techniques from one area might be useful in the other.
It's amazing to think that by studying these abstract mathematical objects, we're potentially gaining insights into a wide range of phenomena in physics and other sciences.
Exactly. And finally, there's the question of how these results might connect to discrete q-difference Fredholm determinants and even to elliptic cluster algebras. These are all areas of active mathematical research, and exploring these connections could lead to a deeper understanding of the underlying structures and symmetries that govern these seemingly disparate fields.
Okay, I think my brain is officially full. We've covered so much ground in this deep dive. It's been an incredible journey exploring the world of q-Painlevé equations.
I agree. It has been a fascinating exploration. We've seen how seemingly abstract concepts like monodromy, tau functions, and parametrices have concrete implications for understanding the behavior of solutions. We've uncovered surprising connections to other areas of mathematics, including conformal field theory, supersymmetric gauge theories, and integral systems. And perhaps most importantly, we've glimpsed the power of mathematical tools and techniques to unravel the mysteries of the universe, both big and small.
I have to admit, I was a bit intimidated by this topic at first, but you've done an incredible job of making it accessible and engaging. Thank you for being such a fantastic guide through this complex mathematical landscape.
It's been my pleasure. Remember, the pursuit of knowledge is a never-ending journey, and today we've taken a significant step forward in our understanding of these fascinating mathematical objects.
To all of you listeners, thank you for joining us on this deep dive. We hope you've enjoyed the journey as much as we have. Until next time, keep those brains buzzing and those curiosity engines running. Welcome to the deep dive. Today we're taking a deep dive into some really cool math.
Yeah.
We're going to be looking at q-Painlevé equations
Oh, yeah.
and their tau functions.
Right.
Specifically, we're going to be looking at a paper
Yeah.
that really focuses on the q-Painlevé Taflé tau function.
Yeah, sounds good.
Our listeners, you guys are math enthusiasts.
Yeah.
So we wanted to pick something that was a little bit, a little bit more
Meaty.
Yeah.
It's fun.
So yeah, why don't you tell us a little bit about q-Painlevé equations?
Well, q-Painlevé equations are sort of similar to their cousins, differential equations, but with a q difference.
Okay, a q difference.
Yeah.
So instead of like smooth changes, you're talking about like jumps, right?
Yeah, jumps dictated by this parameter q.
Okay.
So like
Interesting.
Yeah.
So that q is like it's a scaling factor or something.
it's a scaling factor. Yeah, exactly.
Okay.
Yeah, and so
And these tau functions.
the tau functions are the solutions to these equations. And they're what we call highly transcendental, meaning that we can't really express them with like your typical functions
Right.
like polynomials or exponentials.
Right.
So it's really a pursuit to find them because they're not just like sitting there for you.
Yeah, I was going to say, so that makes it even more complicated, right? Because you can't just like plug in.
Yeah, you can't just plug it into like Wolfram Alpha and hope it pops out.
Right, exactly.
Yeah.
Okay.
And one striking feature of q-Painlevé equations is what we call singularity confinement.
Oh.
So like imagine a solution to the equation and it goes towards infinity, right?
No.
Like a rocket taking off.
Okay.
But instead of just going off into infinity, it kind of comes back down.
Oh, wow.
After a finite number of steps.
Okay, so there's like this, like a hidden order there.
There's this hidden order there. Yeah.
That brings it back.
Yeah.
Okay.
So it's kind of mind-blowing to think about that. Yeah.
Even though it's going off to infinity, it has this like way of coming back.
So instead of attacking these like really complex solutions directly, we're going to be talking about isomonodromic deformations.
Isomonodromic deformations. That's a mouthful.
That is a mouthful.
Yeah.
I'm glad you're here to explain this to us.
Well, from complex analysis, how functions kind of behave when their input goes around special points.
Right.
Right. So that behavior is what we call monodromy.
Okay.
So isomonodromic deformations is a way to look at related systems of equations, but keeping the monodromy constant.
Okay, so the monodromy stays the same.
Exactly, as we kind of tweak some parameters.
Gotcha. So I'm trying to get my head around this whole idea of Q differences.
Q differences.
Can you maybe give me like an example? Like, how is that different from
Yeah.
solving like a regular differential equation?
Sure. So like, the exponential function, right?
Yeah.
It changes smoothly as you increase the input.
But with a Q difference equation, we're
Mhm.
not looking at that smooth change. We're looking at the function like Q times larger
Okay.
or Q times smaller.
So instead of like a smooth curve, it's like
Exactly.
hopping between points.
Hopping between points, yeah.
Okay.
So it leads to like very different solutions.
So it's like instead of like a continuous flow, you're talking about like mathematical hopscotch.
Mathematical hopscotch, exactly.
Okay, right, cool.
Yeah, so this paper we're looking at, it focuses on expressing a specific q-Painlevé I3₃ tau function
Okay.
as what we call a Fredholm determinant.
Okay, now, hold on. I'm seeing a lot of symbols here.
Yeah.
Can you just like break down what a Fredholm determinant is?
Yeah, a Fredholm determinant is a tool from functional analysis.
Okay.
We use it to kind of break down a problem that might seem really hard to solve into like smaller manageable pieces.
Gotcha.
And it helps us to compute determinants of operators.
Okay.
Especially when we're dealing with infinite dimensional spaces, which often happens in the study of differential equations and integral equations.
So it's like we're taking apart like a complex machine.
Exactly.
To see how the
different components work together.
Okay.
Yeah. And in the context of this q-Painlevé III₃ equation, the Fredholm determinant allows us to represent the tau function in a way that we can see its structure.
Okay, cool.
Yeah, and using this determinant, they uncover what we call combinatorial expansions, which are basically a way to break down the tau function into smaller terms.
Okay.
And each term is associated with this visual representation called a Maya diagram.
So we're bringing in diagrams.
Bringing in diagrams, yeah.
Okay.
To help visualize and organize this complex solution.
Now that sounds a little bit more user-friendly.
Yeah, it's surprisingly intuitive.
Okay.
And what's really remarkable is that each of these terms can be expressed in this beautifully factorized form.
Okay, so we've got these tau functions, we've got the Fredholm determinant, we've got these Maya diagrams.
That goes deeper.
Okay, where do we go from here?
We go to what's called Nekrasov functions.
Okay.
These are functions that came about from quantum field theory and string theory.
Hold on, are you telling me that these q-Painlevé equations could tell us something about...
It's still early days.
Okay.
But the connection is tantalizing.
Okay.
It suggests that there might be this like profound and unexpected link between different areas of math and physics.
Okay.
So are you ready to dive in?
I'm ready. Let's dive in.
All right. So
let's start with the heart of this beast.
All right.
This q-Painlevé III₃ equation.
All right. So the q-Painlevé III₃ equation can be written as
GQT2 plus 1 GT2 plus 1.
Where is the function we're trying to find?
Right.
And Q is this parameter that we've been talking about that governs the Q difference steps.
Okay.
And you can see that it involves GQQ, which are the values of the function at these points. Q times larger and smaller than a T.
So that's where the Q difference comes in.
Exactly. That's where that Q difference comes in.
Okay.
So yeah, this is like really highlighting the nature of Q difference equations, where we're concerned with the relationship between the function values that are separated by these jumps.
Gotcha. Okay.
Yeah. So
yeah, it's definitely a unique flavor to these equations.
Yeah.
But folks, remember, we're not after the function directly.
Yeah.
Or after its tau function.
We're after the tau function.
Okay.
And to get there,
okay,
the paper introduces this 2x2 system of linear Q difference equations.
Okay.
So they look like this.
YTPZ, YTZ, 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 YT.
And YTZ is like a 2x2 matrix that depends on T and Z.
Okay.
And L and B are also 2x2 matrices.
Okay.
But their elements are expressions involving GT and its Q-shifted counterparts.
Okay.
And they're given by
LTZ. Begin matrix. Fractures. Begin matrix.
Right.
Plus fracture feeds me plus fracture for Frankie GT plus fracture GT2 fracture GT 2 G quartz fracture GT just fracture GT brain GT for the GT GT.
And these matrices, they basically capture the evolution of the system as we take these Q different steps in both T and Z.
Okay.
And the really important thing is that the matrices L and B contain information about the solution itself.
So it's like we've encoded the q-Painlevé equation into these linear systems.
Exactly. That's a great way to put it.
Okay.
We've encoded it into these linear systems.
Okay.
And this connection becomes even clearer when we look at the compatibility condition on these equations.
So the compatibility condition, what's that?
Yeah, so basically we're just demanding that if we apply the two equations in any order,
Right.
we should get the same result for y qt qz.
Okay.
Right? So it's like making sure our machinery doesn't break.
Right. So like if you run it through one way,
Yeah.
it should be the same as running it through the other way.
Exactly. And it turns out that this consistency requirement leads to a really amazing result.
Okay. What is it?
The compatibility condition is only satisfied if obeys the original q-Painlevé's III equation.
Wow. So it just kind of pops out naturally?
It pops out naturally.
Okay.
So by studying these linear systems, we're indirectly studying the q-Painlevé III equation.
Okay, cool. So, but where does monodromy come in?
So remember, we're aiming for isomonodromic deformations, right?
Right.
So to understand the monodromy of the system, we have to analyze how the solution behaves as z circles around the origin.
Yeah.
And it turns out that within a certain circular strip in the complex plane,
Okay.
these solutions might actually change as we loop around,
Okay.
which means they're not single-valued.
Right?
So this multi-valuedness is captured by what we call a monodromy matrix,
Okay.
and we denote it by M.
So M is kind of like a fingerprint of how the solutions
Yeah.
change as we go around.
As we navigate the complex plane.
Okay.
Yeah, and we can actually express this monodromy matrix in a pretty cool way
Okay.
if we choose the right basis.
Okay, how's that?
So it looks like this,
ME2 pi I sigma 3.
where sigma 3 is a standard Pauli matrix,
Zero 3 begins 0 and 0. 0 minus 1.
N matrix.
And sigma is a parameter that's going to play a big role in our story.
Okay,
And we can actually simplify things a bit more
all right,
by introducing a new variable
okay,
and use sigma.
okay.
And thanks to these monodromy properties, we can express in a more helpful way.
Right, how's that?
So we can write it as...
We're gonna see sigma within that circular strip.
Good.
So what we've done is separate the multi-valued behavior, which is encoded in the sigma 3,
Yeah.
from the single-valued part, which is...
Okay, so we've kind of like untangled the messy bits.
Exactly, from the nice, well-behaved parts.
Yeah. Okay, cool.
Yeah, so now the paper then goes on to talk about parametrices. Parametrices, yeah. These are like simplified systems that capture the essential behavior of our original system near special points.
Okay.
In this case, 0 and infinity.
Okay.
And we denote them by y in 50.
Okay.
And they're defined through what we call auxiliary linear systems.
Okay.
That approximate the behavior of L as z approaches 0 and infinity.
So we're basically zooming in on those specific regions.
Exactly. We're zooming in to get a clearer picture of what's happening there.
Okay.
And the solutions to these auxiliary systems involve these really interesting functions called q-Bessel functions.
Q-Bessel functions.
Yeah.
So are those like
they're similar to
a jazzed up version of Bessel functions?
You could say that they're like the q-difference version of Bessel functions.
Okay.
Yeah.
So these q-Bessel functions, they help characterize the behavior.
They help to characterize the behavior near 0 and infinity.
Okay.
Yeah. And the paper introduces these two ratios.
Okay. What are they?
Phi plus y01, y0, y01, y day, y01, yz.
Okay, so what are those telling us?
So these are comparing the full solution with its approximations near 0 and infinity.
Okay.
So they're capturing the deviation from these simplified solutions as we move away from those special points.
So are they telling us how good our approximations are?
In a sense, yes, but they're also giving us information about the structure of the solution.
Okay.
And the paper shows that for the right choice of parameters, phi plus tz is holomorphic and invertible inside a circle C centered at the origin, while phi is holomorphic and invertible outside of that circle.
So we've got these well-behaved pieces in different domains.
Exactly. We've got the puzzle divided into these two neatly fitting parts.
Okay.
And these ratios, they're going to play a really important role. As we move towards defining the tau function in terms of a Riemann Hilbert problem.
All right. Before we do that, though, let's dig into these q-Bessel functions.
All right. So the q-Bessel functions, denoted by JKOZ, are defined by this infinite series.
Where k is an integer. U is our parameter, q sigma, and z is the variable.
And
you'll notice in the denominator we have these terms
Right.
in QQN,
Right.
those are q-Pochhammer symbols.
Okay, what are those?
So they're defined as
ZQN111 ski.
for a finite n,
Okay.
and when n goes to infinity,
Okay.
we have
so
the
you draw
exact...
Stefan in 1QN.
Oh, for Z1.
Okay.
And these q-Pochhammer symbols, they're like the building blocks in the world of Q-series.
Okay.
Kind of like how factorials are in ordinary calculus.
Gotcha. So these Q-Bessel functions are built from...
They're built from q-Pochhammer symbols, which are built from Q.
Which are built from Q.
So it's Q's all the way down.
Q's all the way down.
Okay, cool.
Yeah, and these Q-Bessel functions are really important for characterizing the behavior near 0 and infinity.
Okay.
For example, the solution to the auxiliary system near 0, which is y0,
Okay.
can be written as left.
Y0 left. 0 sigma DC Q1 2 sigma J2 Q1 2 sigma Q2 sigma Q sigma Q1 2 sigma Q2 sigma Q1 plus 2 sigma Q2 sigma Q1 plus Q2 sigma Q sigma Q2 sigma. Where S0 is are parameters that we choose to make sure phi plus TZ is well behaved.
So you're saying that y0c
Yeah.
is this matrix with Q-Bessel functions as its elements?
Exactly.
And if we tune is 0 correctly,
Yeah.
then phi plus TZ has all the nice properties.
All the nice properties.
So you want,
Yeah.
And similarly, the solution near infinity, which is y under TZ, is also expressed in terms of these Q-Bessel functions,
Okay.
but with different parameters that we
Yeah.
adjust to make sure that phi is well behaved outside of C.
Okay. So what are those telling us?
So those parameters,
Okay.
along with sigma from our monodromy matrix, they actually encode the generalized monodromy data.
The generalized monodromy data.
Yeah,
Okay.
of our system.
Okay.
So they're like the secret code that tells us how the solution behaves globally.
Okay.
Kind of similar to how Stokes data works in differential equations.
Okay. So they're like the key
They're the key,
to unlocking the solution.
Yeah.
Okay.
And a really interesting thing that the paper finds
Okay.
is that these parameters in
Yeah.
SynV are actually Q-periodic functions of T.
Okay. Q-periodic. What does that mean?
That means that SymV, co-SymT, and SymT.
Okay. So as T changes.
As T changes by multiples of Q, these parameters stay the same.
Okay. So that reflects that underlying structure.
Exactly. It reflects that underlying discrete structure
Yeah.
of the problem.
Cool.
Yeah.
Well, it seems like all the pieces are fitting together.
Yeah.
Now, are we ready to move on to that Riemann Hilbert problem?
Yeah, I think we're ready to move on to the next stage.
Oh.
We can reformulate this whole problem as a Riemann Hilbert problem, which will then allow us to define the tau function.
Okay.
So
The Riemann Hilbert problems always sound so mysterious
they are very powerful.
and powerful.
Yeah.
I can't wait to see how they unlock the secrets of this tau function.
Let's do it.
All right, so Riemann Hilbert problems.
Yeah. So remember those well-behaved ratios,
That's right.
and those are going to be really important for our Riemann Hilbert problem.
Okay, so remind me, what exactly is a Riemann Hilbert problem?
Okay, so think of it as a puzzle
Okay.
where you're trying to find a function that jumps across a given contour,
Okay.
and the jumps are determined by those nicely behaved functions.
Okay.
So we have this ratio of these functions, and we call that the jump matrix.
Okay.
And it's given by...
C-1.
So our Riemann Hilbert problem, then, is to find a function, phi
Yeah.
that's analytic both inside and outside of the circle C,
Right.
and whose values on either side of C are related by this jump matrix.
Okay.
So we have...
Phi plus phi is the value just inside C.
Okay.
Phi is his value just outside.
So it's like a continuous function, but with a specific discontinuity.
Exactly.
Okay.
Across the circle.
So we're looking for this mysterious function that behaves differently depending on if we're inside or outside the circle.
Exactly.
And those jumps are dictated by the jump matrix.
That's right.
Which comes from those Q-Bessel function solutions.
Yeah. Yeah.
Okay, cool. So how do we go from this Riemann Hilbert problem
Right.
to the tau function? So this is where things get really interesting.
Okay.
The paper defines the tau function
Okay.
as a Wyndham determinant
A Wyndham determinant.
associated with this Riemann Hilbert problem.
Okay, that sounds a...
It's not as complicated as it sounds.
Okay.
Basically, it's a tool to measure the discontinuity.
Okay, the discontinuity across C.
Across C, that's right.
Okay.
And so the Wyndham determinant is denoted by tau j.
Okay.
And it's defined as...
Tau jgn is tau wj, h plus pi plus j1 plus j pi plus.
So let's break it down.
Okay.
Pi plus is a projection operator
Okay.
that selects the part of a function that only has non-negative powers of z.
Okay.
So essentially, its analytic part inside the circle C.
So it's kind of like filtering out
The well-behaved part.
the well-behaved part near the origin.
Okay.
And H plus is the space of all these analytic functions inside C.
Okay.
And J1 is just the inverse of our jump matrix.
Right.
And dead end means we're taking the determinant of this whole thing. Okay, so we've got the inverse jump matrix.
Yeah.
We've got this projection operator.
Mm-hmm.
We've got this space of analytic functions.
Yeah.
What makes this the tau function?
So the cool thing is
Okay.
that this definition captures the discontinuity of our solution across C.
Okay.
And it turns out that this Wyndham determinant is exactly the tau function of our q-Painlevé III equation.
So we've linked it to the Riemann Hilbert problem.
Exactly.
Which itself comes from those auxiliary systems.
It all ties together.
Okay, cool.
Yeah. And
So,
the paper goes even further
okay.
and rewrites this Wyndham determinant as a block matrix Fredholm determinant.
A block matrix Fredholm determinant.
Okay.
What is that?
So it's a way to represent the determinant in a more explicit form that's easier to compute.
Okay.
And it looks like this.
Shout. Begin matrix, IID and I. Ally talks, where I is the identity matrix.
Okay.
And AK and D are these matrices whose elements are given by...
It's frac and frac plus the smack plus Messiah and whack and smacks plus his I, where and the single valued parts of the solutions in with D respectively.
Okay.
And Z are complex variables.
Okay, so we're bringing in those single valued parts now.
We're bringing in those single valued parts.
Okay.
And this form is actually really helpful because it allows us to use the properties of those q-Bessel functions within psi plus z to actually compute the determinant.
So we're going to get some explicit stuff now.
We're going to get some explicit stuff. Yeah.
Okay. How do we do that?
So the paper expands this determinant into a series of terms.
Okay.
And each term is associated with this visual representation called a Maya diagram.
Maya diagrams. We talked about those in the intro.
We did talk about them in the intro.
Okay.
So a Maya diagram is basically like an arrangement of black and white stones. And each arrangement corresponds to a specific choice of powers of Z in the expansions of A and D.
Okay, so each arrangement is a term.
Each arrangement is a term in the expansion.
And the expansion, okay.
Yeah. And what's really neat is that each term corresponding to a Maya diagram can be written in this nice factorized form.
I like factorized forms.
Factorized forms are nice.
Yeah, they are.
Yeah.
And we've got an even deeper connection, right?
We do.
To some other mathematical concepts.
So these terms are connected to what we call Nekrasov functions.
Nekrasov functions.
Yeah.
Okay.
And those come from quantum field theory and string theory.
So we're getting into physics now.
A little bit of physics, yeah.
What are Nekrasov functions?
So Nekrasov functions are these really intricate objects
Okay.
that capture the contributions of instantons.
Instantons, now we're really in the deep end?
We are in the deep end now.
Okay.
So instantons are basically classical solutions to the equations of motion and gauge theories. And they describe these non-perturbative effects.
Okay.
Which means that we can't capture them with traditional methods.
Okay, so they're tricky.
They're very tricky, yeah.
Okay, so how do they relate to our tau function?
So the key is that when we calculate these Nekrasov functions, there are some combinatorial structures that are the same as the structures we see in our tau function expansion.
Oh, wow. So math and physics?
Math and physics are connected.
Yeah. Amazing.
It's pretty mind-blowing.
Yeah.
Yeah. And the paper shows that each term in the tau function expansion can actually be written in terms of a specific Nekrasov function.
Wow.
And these Nekrasov functions themselves can be written in this really beautiful factorized form.
I like it when things factorize.
Factorization is always nice.
Yeah.
So yeah, it involves q-Pochhammer symbol.
But those Q's keep popping up.
The Q's keep popping up.
Okay.
Yeah. So what does this connection mean?
Right. What does it tell us?
Well, it's a relatively new connection.
Okay.
But it points to some pretty profound implications on the math side.
Yeah.
It suggests that q-Painlevé equations and their tau functions might have a deeper meaning within gauge theories.
Okay. So it's like a new way of looking at these objects.
Exactly. Okay. And on the physics side, it suggests that the tools we use for q-Painlevé equations might actually be useful for understanding the dynamics of these gauge theories.
So we can use the math to help us with the physics.
Exactly. It's a two-way street.
A two-way street. I like it.
Yeah.
Well, this deep dive just keeps getting deeper.
It does.
Can you give us a quick recap of what we've talked about?
Sure. So first we saw that the q-Painlevé, the III equation,
Okay.
can be written as the compatibility condition of this linear system.
Right.
Second, we learned how to reformulate that system as a Riemann Hilbert problem.
Okay.
And third, we found that the tau function is given by this Wyndham determinant, which we can then rewrite as this block matrix Fredholm determinant.
Right. And let's not forget about the Maya diagrams.
The Maya diagram.
And the Nekrasov functions.
The Nekrasov functions, it's all connected.
They're all connected.
Yeah.
Okay.
So now are you ready to explore the connection problem?
The connection problem, what's that?
So the connection problem is understanding how the behavior of the tau function changes as we move between different regions of parameter space.
So we're going to map out how this tau function changes as we tweak these parameters.
That's right.
Okay, I'm ready. Let's map it out.
All right, let's do it.
Okay, so we're going on this mathematical expedition.
Yeah.
We're going to chart the terrain of the tau function.
Yeah, think of it like a map.
Okay.
Of all these different regions.
Okay.
And as we tweak these parameters,
okay,
we're moving between different regions on this map.
So the parameters are like our coordinates.
Exactly. The parameters are our coordinates.
And the tau function is like the elevation depth.
Yeah, the tau function is like the elevation or the landscape.
Okay, so by understanding those singular points.
Yeah, those are like landmarks on our map.
Okay, landmarks.
Yeah.
We can get a sense of
the overall shape.
The overall shape, okay.
Yeah.
So how do we solve this connection problem?
So the paper analyzes the asymptotics.
Okay, asymptotics.
Yeah.
What are those?
So it's basically how the solutions behave as we approach infinity.
Okay.
Or near these singular points.
Right, those landmarks.
Exactly.
Okay.
And from that analysis,
okay,
we can get these explicit formulas.
Okay, formulas for what?
Formulas that relate the tau functions in different regions.
Okay, so we can connect the different parts of the map.
Exactly. We can connect the different parts of the map.
Okay.
And these formulas involve some interesting characters.
Okay, who are they?
Elliptic gamma functions.
Elliptic gamma functions.
Yeah.
Those sound
It's pretty cool.
complicated.
They're a bit complicated. Yeah. But they often show up in problems with modular structure.
Okay, modular structure.
Yeah.
What's that?
It basically means that there are symmetries when we transform the parameters in a certain way.
Okay, so there are patterns.
There are patterns, yeah.
And how things change.
Exactly. And the cool thing is that these connection formulas, they give us this powerful tool for understanding the tau function.
Okay.
And that helps us to understand the solutions to the q-Painlevé equation.
Right. It all comes back to that.
It all comes back to that.
Okay, cool. Well, this has been an amazing journey.
It has been a fun deep dive.
We've gone from like this abstract definition of q-Painlevé equations
to a Riemann Hilbert problem.
The Riemann Hilbert problem.
Combinatorics.
To Nekrasov functions.
And even elliptic gamma functions.
Yeah, it's like we've uncovered this whole mathematical world.
It's all interconnected.
It really is all interconnected.
Yeah.
Well, the paper also mentioned some open questions, right?
Yeah. There's still a lot to explore.
Okay, like what?
Well, for example, they suggest that q-Painlevé equations might have a deeper geometric interpretation within gauge theories.
So even more connections to physics.
Even more connections to physics, yeah.
Okay.
And they also suggest that the techniques we use for q-Painlevé equations might be useful for understanding those gauge theories even better.
So it's like this two-way street.
It's a two-way street.
Of giving and receiving.
Yeah, exactly.
Math helping physics, physics helping math.
That's the beauty of it.
Okay, cool.
Yeah.
Well, this deep dive has been a whirlwind of information.
It has.
And I feel like I have a much better appreciation for q-Painlevé equations now.
I'm glad to hear that.
Thanks for guiding us through this.
It was my pleasure.
Well, that's it for this deep dive.
Yeah.
Into the world of q-Painlevé equations and their tau functions.
Until next time.
We hope you enjoyed the ride as much as we have.
Oh, yeah.
And until next time, keep exploring and keep diving deep. All right, let's take a deep dive into these q-Painlevé equations. You sent over some pretty intense research, and I'm definitely looking forward to breaking it down.
Yeah, these equations are really like puzzles. They're really intricate and complex, and this paper dives into some really advanced techniques to understand them.
Yeah, and from what I've seen so far, we're looking at the A17 q-Painlevé equation, right? And they're using some, I don't know, pretty heavy stuff like tau functions and the Riemann Hilbert problem.
Yeah, exactly. It's not even just about finding solutions. It's more about understanding how they're structured and how they connect to other areas in math.
Okay, well, are you ready to kind of tackle this challenge then?
Absolutely. Let's do it.
Okay, well, let's maybe start with the actual q-Painlevé A17 equation itself. So the paper presents this equation that relates a function g, I guess, at different values. So g of qt, g of t over q, and just g of t. And it involves like squares and fractions. I don't know. It looks pretty complicated.
Yeah, it definitely is. And it's this relationship between the function at different scales, right? Like based on this q parameter that makes it so interesting.
And this q is a deformation parameter, right? So I'm guessing we're going to be kind of looking at how these solutions change as we kind of tweak that parameter.
Exactly, yeah. And the key here is that we're doing it while we keep these important properties constant. And these properties are called the monodromy data. So you can almost think of it like if you have a shape and you want to morph it without actually breaking it or tearing it apart. So we're basically changing the equation, but not really changing its character.
Okay, so let's talk about these monodromy data. What exactly is that, and why is it so important?
Well, imagine you have a solution to the equation and you let it travel around a loop in the complex plane. And the monodromy data basically tells you how the solution changes as it completes this journey. It's kind of like a fingerprint of the solution's overall behavior.
So it's not just like what the solution looks like at one specific point, but how it acts over like the entire complex plane, right?
Right, exactly. And this data is super important to understand how the solution is actually structured. And in this paper, they specifically focus on these parameters like 1it and EC, which are key to their analysis.
So the paper also mentions something called parametrices. And from what I understand, these are kind of like simplified versions of the solution, but I'm not really sure how they make these or even why they're useful.
Yeah, that's a good point. So they're actually built using q-Bessel functions. So they're special functions that have all these interesting properties on their own. And they allow mathematicians to estimate the behavior of the more complete solution, which is really complex in specific regions.
So it's kind of like taking a really big problem and breaking it down into smaller pieces, right?
Exactly. And by using these parametrices strategically, the paper actually sets up this whole framework to tackle the whole complexity of the q-Painlevé equation. But I think the real star here is the Riemann Hilbert problem.
Okay, yes. This is where I start to get a little lost.
It's a pretty powerful idea, but it is abstract. So basically, the paper changes the q difference equation into this problem that deals with how a function behaves when it crosses a specific boundary. In this case, it's a circle.
So instead of trying to solve the equation directly, they're kind of translating it into a different mathematical language. What's the advantage of doing that?
Well, it gives you a whole new perspective, right? It opens up all these techniques for analyzing the solution. You know, imagine you're looking at a sculpture and you look at it from different angles to fully understand what it looks like, right?
Okay, so that is where the tau function comes in, right? And it's defined by something called a Wyndham determinant, which also sounds kind of scary.
It's not as bad as it sounds.
Yeah.
So this tau function, it holds all this crucial information about what happens in the Riemann Hilbert problem. So you remember that circle boundary we talked about. The tau function tells you exactly how much the function changes when it crosses it.
So it's like a detective figuring out how the solution behaves at this important boundary.
Exactly. And what makes it even more interesting is that the paper shows that this tau function is directly connected to the solution of the original q-Painlevé equation.
Okay, so now we're getting somewhere. How do they make this connection? What's the secret?
Well, they use this really cool trick. It's called the Beckland transformation. You can think of it like if you have a recipe and you can use it to create a brand new dish from an existing one.
So they're not just finding one solution, they're creating a whole bunch of solutions, right?
Right. And the crazy part is they actually prove that if you take two tau functions, one from the original solution and one from the transformed solution, and you look at their ratio, it's directly related to the solution of the q-Painlevé equation.
That's pretty wild. So they found this hidden link between this abstract tau function and the actual solution we're looking for.
Yeah, it's pretty cool. And they do it by really carefully looking at how the tau function, which is a determinant, changes under this Beckland transformation. It's like a step-by-step process where they track how each part of the transformation affects the determinant. And in the end, they reveal this relationship between the ratio of the tau functions and what we call the q-Painlevé transcendent, which is the solution we want.
That sounds like a super detailed process, like you need to be a master of determinants and transformations and all that.
Exactly. But that's not all. They go even further. They derive something called a bilinear relation involving this tau function.
Okay. What is that? What does that tell us? Why is it important?
Well, it's this equation that connects the tau function at different values of dit. And it's like the secret code that controls how the tau function and ultimately the solution itself behaves.
So they're not stopping at just finding the connection. They're going even deeper to understand what's going on underneath.
Exactly. Yeah. And this bilinear relation, it's like this powerful tool to analyze what the tau function can do and, in the end, understand the solution of the q-Painlevé equation. But they don't stop there. They also look at the structure of the tau function itself and express it as a sum of terms labeled by these things called Maya diagrams.
Maya diagrams, those sound pretty cool. What are those and how do they help us understand the tau function?
You can think of them as blueprints, like in architecture. Each Maya diagram represents a mathematical object, and all of these objects, when put together correctly, give you the tau function. It's like building something complex out of simpler parts.
So they're basically breaking down this complicated function into smaller, easier to understand parts.
Right. And what's really cool is that they connect these Maya diagrams to these things called Nekrasov functions, and those come from a totally different area of math theoretical physics.
So they're using physics to understand this purely mathematical concept. It really shows how everything is connected.
Totally. And this connection to Nekrasov functions gives us a deeper understanding of the structure of these combinatorial expansions. It even reveals some hidden symmetries and links to other parts of math.
It's like they're finding these secret pathways between different areas of math.
Yeah, that's a great way to put it. And the paper doesn't stop there. They actually explore different representations of the tau function. It's super versatile, and they show how it connects to all sorts of mathematical ideas like symmetric functions and Toeplitz determinants.
Wow, so the tau function is like a real key player here, huh?
Definitely. And by understanding it, we gain a much better understanding of the q-Painlevé equation itself. But before we dive into the nitty-gritty of the proof, I think it would be helpful to just step back and take stock of everything we've talked about so far.
Okay, so just to recap, we've looked at the q-Painlevé A17 equation,
Yeah.
talked about this really interesting tau function, and touched on the Riemann Hilbert problem and these combinatorial expansions.
Exactly. And we've seen how all these abstract ideas are actually super connected, revealing this intricate structure of the solution and its connection to other areas of mathematics.
But I have a feeling we've only scratched the surface. There's so much more to explore, especially when it comes to the details of how they prove this connection between the tau function and the solution of the q-Painlevé equation.
You're absolutely right. Are you ready to go deeper and see how they actually put all these pieces together?
Absolutely. Let's continue this mathematical adventure and see where it takes us.
Uh,
All right, so we've kind of set the stage, talked about these q-Painlevé equations, the tau function, and this Riemann Hilbert problem. But now I'm ready to get into the nitty-gritty. How do the authors actually connect all these ideas to find the solution?
Well, the heart of their proof really lies in understanding how the tau function transforms. Remember, it's defined as a determinant, and they carefully analyze how this determinant changes under the Becklin transformation.
Right, right. Can you remind me again what's so special about this Becklin transformation?
Sure, it's this incredibly powerful tool. It's like having this magic wand that takes one solution to the q-Painlevé equation and, poof, transforms it into a completely new solution. It's like planting a seed and watching a whole garden of solutions bloom.
Okay, yeah, I'm starting to remember. So it's not just about finding one answer, but about understanding how different solutions relate to each other.
Exactly. It's about uncovering this hidden structure within the world of these equations, like revealing the secret connections in a complex network.
Okay, that makes sense. But how does the tau function, defined as a determinant, how does that fit into all of this?
Well, remember, the tau function is derived from the jump conditions in the Riemann Hilbert problem, right?
Yeah.
It's a determinant that describes those jumps.
Right, those jumps that happen when the function crosses that circle boundary.
Exactly. Now, when you apply this Becklin transformation, it tweaks those jump conditions. And because the tau function is based on those conditions, it changes too.
So they're basically watching how this tau function, this determinant, morphs as they apply this transformation that generates new solutions.
Precisely. And this is where it gets really interesting. They show that the ratio between the original tau function and the transformed one is directly linked to the solution of the q-Painlevé equation itself.
Oh, wow. So they're connecting this abstract tau function to the actual concrete solution we're looking for. It's like they've built this bridge between two different worlds.
That's a great way to put it. It's like they've found the secret passage that connects these two seemingly separate things. And they do all of this by painstakingly analyzing how this determinant changes step by step under the transformation. It's very intricate work.
Yeah, it sounds like you'd really need a deep understanding of determinants and all these transformations to even begin to understand what they're doing.
Absolutely. But the payoff is huge. They essentially reveal this beautiful relationship between these tau functions and the solution we're after. But they don't stop there. They go a step further and derive what's called a bilinear relation that involves this tau function.
A bilinear relation, I have to admit, that sounds a bit intimidating.
Yeah.
What exactly is that, and why is it so important?
It's a bit technical, but essentially it's an equation that connects the tau function at different values of dest. And it's like cracking a code. This equation reveals how the tau function behaves, and since the tau function is tied to the solution, it also tells us a lot about the solution itself.
So they're not just satisfied with finding a connection, they're digging even deeper to understand the underlying mechanics of it all.
Exactly. It's like they're not content with just knowing that the clock works. They want to take it apart and see all the gears and springs and understand exactly how everything fits together.
Okay, that's a great analogy. So we've got this Becklin transformation, these tau functions changing, and then this bilinear relation to help us understand it all. What about those combinatorial expansions we talked about earlier? Where do those fit in?
Yes, those are really crucial too. Remember the Maya diagrams and those Nekrasov functions from physics? Well, those expansions allow us to actually calculate the tau function. They break it down into these manageable pieces, each represented by a Maya diagram. It's like taking a complex image and breaking it down into pixels.
Okay, so it's a way to visualize and actually compute this tau function. And what about those Nekrasov functions? How do they come into play?
Well, it turns out that the coefficients in these expansions are directly related to those functions from theoretical physics. It's a really remarkable connection.
So again, we're seeing these links between seemingly different areas of math. It's like this hidden web connecting everything.
It really is. And this connection to Nekrasov functions doesn't just help us understand the structure of these expansions, it also opens up the possibility of applying these findings to physics as well. It's really exciting stuff.
This is all incredibly fascinating. But I'm also realizing how complex this all is. We've got so many different pieces working together here.
Absolutely. This research is pushing the boundaries of what we know about q-Painlevé equations. It's not just about finding solutions anymore. It's about developing entirely new tools and frameworks that can be applied to a whole range of mathematical problems.
So it's not just about solving one specific equation. It's about expanding our mathematical toolkit and gaining a deeper understanding of the bigger picture.
You got it. And this paper is a perfect example of that. It shows the power of combining different branches of math like analysis, algebra, and even combinatorics to solve some really tough problems.
Well, I have to say, I'm hooked. I'm ready to dive into the specifics of their proof and see how they actually manipulate these determinants and expansions to get their results.
All right, let's do it. Are you ready to witness some real mathematical magic? We're about to get into the nitty-gritty of their calculations and see the beauty behind their approach.
Absolutely. Let's continue this journey and unravel the mysteries of the q-Painlevé A17 equation. All right, so we've spent some time understanding the main concepts at play here. The q-Painlevé A17 equation, the tau function, this Becklin transformation, and even those combinatorial expansions. But now I really want to see how it all comes together. How do they actually prove their results?
This is where it gets really exciting. The authors really flex their mathematical muscles here, and they show how the tau function and its transformations hold the key to unlocking the solution of the q-Painlevé equation.
One thing I'm still a bit fuzzy on is this whole idea of isomonodromic deformations. We're basically changing the parameters of the equation, but we're keeping the monodrony data constant, right? Those kind of fingerprints of the solution.
You got it. Imagine a potter molding clay. The shape of the pot changes, but the essential properties of the clay remain the same. So we're deforming the equation, but we're not fundamentally changing its character.
Okay, yeah, I see the analogy. So as we tweak the parameters, the tau function changes too, right? It's like it's following the solution as it evolves.
Exactly. And the authors managed to derive a formula for exactly how the tau function changes under these deformations. And that's a really big step in connecting it to the solution.
So by understanding how the tau function transforms, we get clues about the solution itself. But how do they even begin to calculate these transformations? I mean, it seems incredibly complicated.
This is where they introduce a really powerful tool. It's called the Fredholm determinant representation of the tau function. They basically express the tau function as a determinant of a certain operator.
Okay, I have to be honest. The term Fredholm determinant doesn't exactly make me feel warm and fuzzy. Can you maybe break that down a bit? What is it and why is it so useful?
Sure, imagine a matrix, but instead of having a finite number of rows and columns, it's infinite. That's kind of what we're dealing with here. And the Fredholm determinant gives us a way to handle these infinite dimensional objects. It lets us use tools from functional analysis, which is a branch of math that studies functions, to understand the tau function.
So it's like using a really powerful microscope to look at this tiny but incredibly complex object.
Yeah, that's a good way to think about it. And the results they get are really impressive. They come up with these explicit formulas for the Fredholm determinant. And these formulas reveal all these connections to other areas of math, like this thing called the generalized Séguin formula, which comes from the theory of Toeplitz determinants.
Man, it's amazing how all these different branches of math are connected in this paper. It's like a giant puzzle where all the pieces fit together in this unexpected but beautiful way.
That's what's so cool about math, right? It's all connected. The authors use tools from functional analysis, operator theory, complex analysis, all to help us understand this one object, the tau function.
So we've got isomonodromic deformations, the tau function, Fredholm determinants, Séguin formulas, all these pieces working together to crack this q-Painlevé A17 equation. What about those combinatorial expansions? Do those play a role in this part of the proof too?
Oh yeah, definitely. Those expansions with those Maya diagrams and connections to Nekrasov functions, they give us another way to look at the tau function structure. The paper goes even deeper into them and shows some really interesting combinatorial and algebraic properties.
I remember you mentioned that the coefficients in those expansions are connected to certain symmetric functions. Can you remind me what that's all about?
Sure. So symmetric functions, they're these special mathematical objects that don't change when you rearrange their variables. And it turns out the coefficients in those expansions can be expressed using these symmetric functions. It reveals this underlying algebraic structure within those expansions.
So it's like they found a secret code, a language of symmetry that governs the tau function.
That's a great way to put it. And this connection to symmetric functions doesn't just help us understand the tau function better, it also hints at potential applications in other fields of math, like representation theory or algebraic combinatorics.
It's incredible how they've managed to weave together so many different ideas from different fields of math. Analysis, algebra, combinatorics, even physics. It's really a testament to their creativity and skill.
I agree. It's really a beautiful piece of work.
I'm just blown away by the depth and scope of their work. It's not just about solving one equation. They've given us all these new tools and a much deeper understanding of the whole world of q-Painlevé equations.
Absolutely. This research really pushes the boundaries of what we know, and it opens up so many exciting possibilities for future research.
Well, I've got to say, this has been a truly fascinating deep dive. I've learned so much about q-Painlevé equations and the amazing math that goes into understanding them.
It's been a pleasure talking about it with you. It's always exciting to explore these complex mathematical ideas and see how they connect to different areas of math and even physics.
Thanks for joining us on this mathematical adventure. We hope you've enjoyed exploring the world of q-Painlevé equations with us. Until next time, keep those mathematical minds buzzing and keep exploring the beauty and wonder of math. All right, let's jump into this paper you brought today.
Okay.
The title is Riemann Hilbert Problems, Fredholm Determinants, Explicit Combinatorial Expansions, and Connection Formulas for the General q-Painlevé III₃ tau functions.
Yeah.
Quite a mouthful,
Yeah.
but I'm ready for the challenge.
Lots to unpack.
Yeah, so before we get lost in the weeds, can you remind me why q-Painlevé equations are so important? What makes them special?
Well, they're difference equations.
Okay.
So they describe how a function changes in discrete steps
Right.
rather than continuously.
Uh-huh.
So they're kind of like the discrete counterparts to the more famous Painlevé differential equations.
Yep.
And those pop up everywhere, like physics and engineering and even finance.
Yep.
And the interesting thing is that these q-Painlevé equations also appear in lots of different fields.
Yeah.
So they connect these seemingly different areas of math.
Oh, I like that. Okay, so they're like these mathematical bridges linking different concepts together. I always find that fascinating. But where do these tau functions come in? I remember them from some of my more advanced math classes, but I'm a bit fuzzy on the details.
Well, tau functions are essentially a way to represent the solutions to these equations in a more manageable form.
Okay.
They're powerful tools that let us study the often very complex behavior of these solutions.
Got it.
Think of them as the keys to unlocking the secrets of these equations.
I'm intrigued. So this paper we're looking at, it focuses on one specific q-Painlevé equation, right? What's special about it?
Yeah, it focuses on the q-Painlevé equation known as A17.
Okay.
And it's given by this formula, G22 plus T, GT2 plus 1.
Wow. That equation already looks like a challenge. It reminds me of those recursive sequences we used to play with in discrete math, but on a whole other level. So how does this paper actually tackle this thing? What tools do they use?
Well, they take a very clever approach. They start by reformulating this q-Painlevé equation as a Riemann Hilbert problem.
Riemann Hilbert problem. That rings a bell. It has something to do with finding a function with specific jumps, right? Like navigating a mathematical obstacle course in the complex plane.
That's it.
Okay.
A Riemann Hilbert problem basically asks us to find a function that satisfies certain conditions along specific contours in the complex plane.
Got it.
And these conditions usually involve prescribed jumps or discontinuities in the function's values as we cross these contours.
So they've essentially translated this q-Painlevé equation into a different language, this Riemann Hilbert problem framework. But how does that help solve it? What's the advantage of doing that?
Well, it's all about using the right tools, right?
Right.
By transforming the problem into a Riemann Hilbert problem, we can use a lot of powerful techniques developed for this type of problem. One of these tools is something called a Fredholm determinant.
Fredholm determinant. Now, that's a name I haven't heard in a while. I vaguely remember them from my functional analysis days. Can you remind me what they are and why they're useful here?
Sure. So think of a Fredholm determinant as a way to measure the size or impact of an operator. And in this case, the operator comes from the jump data of the Riemann Hilbert problem, which basically describes those jumps or discontinuities we were talking about.
So we're extracting information about these jumps and encoding it into this Fredholm determinant. But how does that connect back to the original q-Painlevé equation? It seems like we've taken a detour into a different area of math.
That's the beauty of it. The paper proves that this Fredholm determinant satisfies special equations called bilinear relations. And these relations involve products of two tau functions. And it turns out these bilinear relations are actually equivalent to the original q-Painlevé equation.
Wait, hold on. Let me make sure I'm following. We started with a q-Painlevé equation. We transformed it into a Riemann Hilbert problem, and then we constructed this Fredholm determinant from its jump data. And now you're saying that this determinant satisfies relations that are equivalent to the original equation. It's like we've come full circle, but from a new angle.
You got it.
Wow, okay.
It's like we found this hidden tunnel that connects two separate worlds. And this connection is really powerful because it lets us study the solutions to the q-Painlevé equation using these tools and techniques from Riemann Hilbert problems and Fredholm determinants.
I'm starting to see how brilliant this approach is.
Yeah.
But didn't you also say that tau functions are key to understanding these equations?
Yeah.
Where do they fit in here?
Oh, they're at the center of it all. Remember those bilinear relations we were talking about?
Yeah.
Well, they involve products of two tau functions. And this paper actually goes even further. It provides explicit combinatorial expansions for these tau functions.
Combinatorial expansions. So we can express these tau functions and therefore the solutions of the q-Painlevé equation in terms of simpler building blocks.
Yeah, exactly. It's like you have this complex puzzle and you figure out how to assemble it from individual pieces. In this case, the pieces involve these concepts called Maya diagrams and Nekrasov functions.
Maya diagrams and Nekrasov functions. Okay, now you're really testing my math vocabulary. Can you explain what those are and why they're important here?
Okay, so imagine a sequence of pluses and minuses. Like a code. A Maya diagram uses this code to represent a partition of an integer. For example, you could have a plus followed by two minuses to represent the partition of 3 into 1 plus 2.
So each Maya diagram represents a different way of breaking down a number. That's a neat way to visualize it. But how do these Nekrasov functions come into play? They sound a bit more intimidating.
Yeah, they're a bit more involved, but basically they provide a way to calculate the contribution of each Maya diagram to the overall tau function.
There are these special functions that show up in math and physics, including gauge theory. Don't worry too much about the specifics right now. The important thing is that these Nekrasov functions give us a way to quantify the impact of each Maya diagram on the solution.
So we're basically combining these Maya diagrams, which provide a visual way to represent partitions, with these Nekrasov functions, which give us a way to calculate their contributions to construct the tau functions and ultimately the solutions to the q-Painlevé equation. It's like a recipe with these fascinating ingredients.
I like that. That's a great analogy. It's like a chef combining different ingredients to create a complex dish.
Yeah.
And the paper provides the exact recipe. It gives us specific formulas to calculate each term in the tau function expansion.
Wow. Okay.
Based on the corresponding Maya diagram and Nekrasov function.
This is really mind-blowing. They've provided a blueprint for constructing these solutions using these combinatorial building blocks. This is way deeper than I imagined. I think we need a moment to let all of this sink in before we go on. Yeah, sounds good.
Let's
We've covered a lot.
Yeah, we covered a lot already. Okay.
Yeah.
I think I've caught up with everything for the first part.
Yeah.
We saw how this paper tackles the q-Painlevé III₃ equation.
Yeah.
Using Riemann Hilbert problems, Fredholm determinants, and these combinatorial expansions with Maya diagrams and Nekrasov functions.
Right.
But there's even more to explore.
Yeah, we've only just started.
Okay.
We've been talking about these tau functions, which are key to understanding the solutions of the q-Painlevé III equation.
Yeah.
And now this paper goes even deeper, looking at how these tau functions behave
Okay.
under certain transformations.
Transformations, like mathematical operations that change how we look at these functions. Tell me more.
So the paper looks at a specific type of transformation called a Beckland transformation.
Okay.
Think of it as a way to generate new solutions to the q-Painlevé equation from the ones we already have.
Okay.
Like a recipe that takes one solution
Right.
and gives you another one.
Okay. So we're playing with these solutions, twisting and turning them to find hidden connections. I love how this paper keeps showing these relationships between different math concepts. But how do these Beckland transformations work? What do they do to these tau functions?
Well, the paper shows that when we apply a Beckland transformation to a tau function,
Okay.
we get a new tau function that's related to the original one in a certain way.
Okay.
It's like looking at the same thing, but from a different angle,
Right.
revealing new features and symmetries.
Okay, I'm picturing it like a kaleidoscope. We turn it a bit, and the same pieces make a new pattern. But this isn't just about pretty patterns, is it? What's important about these transform tau functions? What do they tell us?
They give us a lot of information about the structure of the solution to the q-Painlevé equation.
Okay.
For example, the paper shows that the ratio of the original tau function to its transformed version
Okay.
is related to the q-Painlevé transcendent itself.
Wait, so we're not just expressing the solution with tau functions, but are also seeing connections between them and the equation. It's like the tau functions are these middlemen showing us the hidden structure of the equation.
Exactly. It shows how these different pieces of the puzzle fit together.
Yeah.
But the paper doesn't stop there.
Okay.
It introduces auxiliary systems
Okay.
to analyze the behavior of the solution in different regions.
Auxiliary systems. Sounds interesting, but also kind of complex. Can you give me a simple explanation of what these systems are and why we need them?
Well, remember we said that the solutions can look different
Yeah.
depending on where we're looking.
Right.
These auxiliary systems let us approximate how the solutions behave
Okay.
in specific regions,
Okay.
especially around 0 and infinity.
So they're like simplified versions of the original problem, kind of like zooming in on a map to get a more detailed view of a specific area.
Exactly.
Okay, cool.
Then we can actually express the solutions to these auxiliary systems
Uh-huh.
using well-known functions called q-Bessel functions.
q-Bessel functions. I've seen those before. They're everywhere in mathematical physics.
Yeah.
But how do these q-Bessel functions and these auxiliary systems relate back to the original q-Painlevé equation and its tau functions?
Okay, so the paper introduces these special ratios denoted by high plus and a,
Okay.
which are basically the original solution divided by the solutions from these auxiliary systems.
Okay.
And they encode the monodromy data.
Parametrices, monodromy data, getting a bit technical. Can you break down those terms and explain why these ratios matter?
Think of parametrices as bridges between the original problem and the simplified ones, those auxiliary systems. They capture the important information about the solution in different regions.
Yeah.
And monodromy data tells us how the solutions behave as we move around singular points.
Okay.
Those are points where the solutions might act up.
So these parametrices, built from the solutions to the auxiliary systems, help us understand how the solutions to the q-Painlevé equation behave in different regions, particularly around those tricky points. Like they're giving us a map of the solutions.
Yeah, exactly.
Right.
And what's interesting is that these parametrices, or ratios,
Okay.
are well-behaved in specific regions.
Okay.
For example, Eleta plus is holomorphic and invertible inside the unit circle
Okay.
in the complex plane,
Okay.
meaning it's smooth and well-defined in that region.
Holomorphic and invertible. So they're following all the rules and behaving well in those regions.
Yeah, that's one way to put it.
Okay.
And similarly, LA has the same properties outside the unit circle.
Okay.
So by looking at these well-behaved ratios, we can learn a lot about the original solution, even where it might be tough to study directly.
Okay, I'm seeing how powerful this is. By breaking the problem down into smaller parts and studying these well-behaved ratios, we're getting a better understanding of the overall solutions.
Right.
It's like putting together a puzzle one region at a time.
Exactly.
Okay.
And there's more.
Oh, great.
Remember those parameters N0 and AA?
Yeah.
That appear in the solutions to the auxiliary systems.
Right, those parameters, they control how the solutions behave, right?
Yeah.
What's special about them?
Well, the paper shows that they are q-periodic functions of t,
Okay.
the independent variable in our q-Painlevé equation.
Okay.
This means they repeat
Okay.
as we move along the t-axis with a period determined by q.
So even these parameters have interesting properties connected to the equation. It's like everything in this math puzzle is linked.
Exactly.
That's really neat.
And it's not just periodicity.
Yeah.
The paper shows that we can actually adjust the signs of these parameters
Okay.
so that they stay the same under a q shift in AT. They don't change even when we move along the t-axis in steps of q.
So they're like these fixed points, unchanging even when things around them are changing. That's pretty cool.
Yeah, they give us great insights into the behavior of the solutions. They're like signposts in this math world.
Yeah.
But those aren't the only invariants the paper looks at.
Correct.
There's also CT, which appears in the limits of A+, and it's defined in terms of that function g that we're trying to solve for.
Okay, so another thing linked to the solution. What about CT? Does it stay the same too?
It does.
Okay.
The paper shows that CT stays the same under a combination of transformations, a Becklin transformation, and a shift in t.
So even when we're changing things and making new solutions, some things stay constant, like those constants in the universe, unchanging in all the chaos.
Exactly.
Okay, awesome.
These invariants are like anchors.
Yeah.
They help us understand these q-Painlevé equations, and they connect different solutions and help us understand the overall behavior of these math objects.
This is really fascinating stuff.
Yeah, it
We've covered so much.
I know.
Should we move on
Let's do it.
to part 3?
Yeah, we'll talk about connection formulas.
Okay, I can't wait. All right, we're back for the last part of this deep dive.
Yeah, the final stretch.
We've explored q-Painlevé equations,
Right.
learned about tau functions.
Uh-huh.
We've seen Becklin transformations and these invariant quantities.
It's been quite a journey.
It really has.
But there's one more piece.
Yeah, you've been teasing it this whole time.
Connection formulas.
Yeah.
The connection formulas.
So tell me, what are they? How do they tie everything together?
Well, connection formulas are basically the bridges between different solutions to the q-Painlevé III equation.
Okay.
They provide a roadmap
Okay.
to navigate between these solutions that might seem separate and help us understand how they relate to each other.
So like translators between mathematical dialects, helping us see how solutions that look different are actually connected.
Exactly.
Okay, cool.
Understanding these connections is really important to get the full picture of how the solutions behave.
Okay.
It's like putting together a world map
Right.
from smaller maps.
Okay, I see why these connection formulas are so important. They're like the missing pieces that help us see the whole picture. But how does this paper find them? Where do we even start looking for these connections?
Well, the paper uses those auxiliary systems we talked about before.
Right, those systems that helped us understand the solutions around 0 and infinity. Those areas that can be a bit tricky.
Exactly. Okay. Remember, those systems had solutions with q-Bessel functions.
Yeah, those functions that are all over mathematical physics.
Yeah, the paper uses those q-Bessel function representations to figure out the relationships between the tau functions for different solutions to the q-Painlevé III equation. They look at what happens to the tau function under a transformation that flips the variable t to its reciprocal, 1t.
So they're looking at how the solution changes when we invert the variable. Yeah. Kind of like flipping the equation inside out.
Yeah, you got it.
Okay, cool.
And this leads to some interesting insights.
Okay.
They get a formula
Okay.
for how the q-Painlevé transcendent transforms under this 1T mapping.
So they're not just messing with the variable, they're seeing how it changes the solution itself. And since tau functions are tied to the transcendent, I'm guessing this transformation also affects them?
You're right.
Okay.
The paper has a formula,
Oh,
a connection formula,
right.
that shows how the tau function transforms under this 1T operation.
Correct.
And this formula uses those 0 and C's parameters from before
Correct.
and something called elliptic gamma functions.
Elliptic gamma functions, those sound kind of exotic. Can you explain those to someone who isn't an expert?
Well, elliptic gamma functions are special functions that show up in different areas of math,
Okay.
usually with elliptic curves and modular forms.
Okay.
They're like building blocks for understanding symmetries and transformations.
Okay.
And in this connection formula, they show us the relationship between the original tau function and its transformed version.
So these connection formulas aren't just linking solutions, they're also bringing in these other cool mathematical objects like elliptic gamma functions. It's like they're weaving together all these different parts of math.
Exactly.
Okay, amazing.
It shows how connected math is, how different ideas can come together in really unexpected ways.
I like that.
And speaking of connections, the paper also talks about fusion kernels.
Fusion kernels. Okay, this is a lot to take in. But keep going. What are fusion kernels?
Okay, so imagine we have these building blocks called conformal blocks. They come from conformal field theory, which describes systems with special symmetries.
And these conformal blocks have really interesting properties.
Okay.
And they're related to the tau functions we've been talking about.
So they're like relatives of our tau functions, hanging out in this world of conformal field theory, a world where things can change shape but still keep their essential properties.
Yeah.
But what do these fusion kernels do?
Fusion kernels describe the relationship between different types of conformal blocks. Think of them as the glue that holds these blocks together, letting us combine them in different ways.
Okay, but conformal field theory seems pretty abstract. Can you give me a more concrete idea of what these conformal blocks are? What do they represent?
You can think of them as math objects that encode the correlation functions of a conformal field theory. These correlation functions tell us how different parts of a physical system are related. And the fusion kernels tell us how these relationships change when we combine these conformal blocks. So we're not just studying these blocks individually, we're also looking at how they interact and change when we put them together. It's like studying how these mathematical objects connect and influence each other.
That's a great way to think about it.
Okay, cool.
And the paper actually gives us formulas for these fusion kernels in the context of Q-deformed conformal blocks for cases where the central charge is infinite and where it's equal to 1.
Central charge, another new term for me. What's that? Why does it matter?
So the central charge, it describes the symmetry of the conformal field theory. It's a way to measure how complex the theory is. A higher central charge usually means more symmetries. And the paper shows that even when we have this Q deformation, these fusion kernels still have nice explicit representations.
So even when we change the conformal field theory a bit, these kernels still behave well and have these elegant mathematical forms, like they're adaptable, keeping their core traits, even as we change things around them. Okay, that's amazing.
It shows how strong these math concepts are and how connected different areas of math can be.
We've gone from Riemann Hilbert problems to Fredholm determinants, combinatorial expansions, Becklin transformations, connection formulas, and now fusion kernels. It's incredible how everything's connected in this mathematical world.
It really is.
This deep dive has shown me how intricate and interconnected math is.
Right.
It's like exploring a huge landscape.
Yeah.
Finding hidden paths and connections.
Yeah, I agree.
And who knows what else is out there.
Yeah, this paper opens up so many possibilities. It shows how we can use tools from different areas of math to understand these q-Painlevé equations and their tau functions.
It's really inspiring to see how creative mathematicians are, pushing the boundaries of what we know and showing the beauty and elegance of math.
Exactly.
This was a great journey.
It was.
Thanks for taking us on this deep dive.
Of course. Glad you enjoyed it.
I can't wait to see what's next.
Me too.
Until then, keep exploring.
And keep those brains thinking.
All right. That's it for today.
Thanks for listening, everyone.
Welcome, everyone. Ready to dive into the world of q-Painlevé equations.
Always ready for a good mathematical deep dive.
Today, we're taking a close look at a pretty fascinating paper. It's called Riemann Hilbert Problems, Fredholm Determinants, Explicit Combinatorial Expansions, and Connection Formulas for the General q-Painlevé III tau functions.
Quite a mouthful.
It is. But don't worry, we'll unpack it all bit by bit.
We'll break it down into manageable pieces.
Absolutely. And for those of you familiar with, complex analysis, special functions, this is going to be right up your alley.
Yes, definitely geared towards an expert audience.
So before we get into the nitty-gritty, maybe just a quick overview of what makes Painlevé equations so special.
Sure. So Painlevé equations, they're a class of nonlinear differential equations, and they have this really unique property called, well, the Painlevé property.
Catchy name.
Right. Basically, the only movable singularities their solutions can have are poles.
Okay, and why is that so significant?
It's a big deal because this property is tied to this idea of integrability, meaning we can, in theory, solve these equations analytically.
Ah, so it hints at a deeper structure, a way to crack the code.
Exactly.
Now, this paper we're looking at, it focuses on a specific type of Painlevé equation, the A1-7, and its q-deformed version.
Right. That's right. The q-deformed version, well, it introduces this quantum parameter, q, and it changes things up a bit.
Changes how?
Instead of continuous derivatives, you have q differences.
Which are like, what, discrete versions of derivatives?
Exactly. Think of it as discretizing the system in a specific way.
Interesting. So what's the big deal with this q deformation? Why bother?
It unlocks a treasure trove of new mathematical structures and connections. We see links to Riemann Hilbert problems, Fredholm determinants, combinatorics.
Combinatorial, so like patterns and arrangements.
Exactly. Plus special functions and even gauge theory.
Gauge theory from physics, right?
One and the same.
Okay, I'm starting to see how deep this rabbit hole goes. We're starting with this one equation and branching out in so many directions.
That's the beauty of it.
So let's start with the equation itself, the q-Painlevé III. What's it look like?
Here it is. G equals gt squared plus t divided by gt squared plus 1.
Okay, that's, yeah, a bit dense.
And like other Painlevé equations, this one pops up from the compatibility condition of two linear q-difference equations.
So we're looking at a linear system instead of tackling the nonlinear equation head-on.
You got it. These linear equations, they involve two matrices, LTZ and BT.
Okay, and what's this compatibility condition all about?
It means the order you apply these linear equations in shouldn't matter. And when you impose that requirement, bam, you get the q-Painlevé equation.
So it's hidden within this linear system waiting to be revealed.
Precisely. And this link to the linear system is a game changer. We can now use tools from linear algebra and complex analysis to understand this nonlinear beast.
So it's like we're finding a back door into the problem, a clever workaround.
Exactly. Now, the paper also brings up this idea of isomonodromic deformations.
Isomonodromic. What now?
As you tweak the parameter t in these linear equations, you're deforming the system. But some things stay the same. The monodromy data.
Hold on. Monodromy data.
Think of taking a solution to the system and letting the variable z travel around a closed loop in the complex plane.
Okay, so we're tracing a path.
Right. The monodromy data tells you how the solution changes as z goes around this loop. It's like a global snapshot of the solution's behavior.
So even as the system changes with t, this monodromy data stays constant.
Exactly. That's the isomonodromic bit. And it's key to connecting the q-Painlevé equation to powerful tools like the Riemann Hilbert problem.
We'll get to that. But first, there was something about a Becklin transformation. What's that all about?
Ah, the Becklin transformation. Think of it like a symmetry of the equation. It shows us how to link different solutions.
Like a map between solutions.
Exactly. In this case, it's g tilde of t equals the square root of t divided by g of t, where gt is one solution and g tilde of t is another.
Interesting. So it's a way to generate new solutions from existing ones.
And what's cool is that it doesn't just act on the equation itself, but also on the linear system through some specific matrices.
Okay, so it's a symmetry that goes deep, respects the structure of the problem.
Absolutely.
Okay, let's circle back to monodromy. You said it describes how solutions change when z goes around a loop in the complex plane. How do we actually analyze that?
The paper gets clever here. They build solutions within a circular strip in the complex plane. Then they look at how these solutions change as we go around that circle using a monodromy matrix M.
So this matrix M captures the essence of how the solution behaves globally.
Exactly. And there's this thing called the determinant of the solution, denoted by YTD, and it holds key information about this monodromy matrix.
So it's all connected, these determinants, matrices, monodromy.
It all fits together. Now, did you notice the paper mentions q-Bessel functions?
Yeah, I was wondering about those. What's their role?
They pop up naturally when you analyze the behavior of the solutions near 0 and infinity. They come from approximating the full linear system with simpler ones called auxiliary systems.
So we simplify to understand the extremes, the behavior at the edges.
Right. And these q-Bessel functions, they're special functions, and they help us grasp the asymptotic behavior of the solutions.
I see. Now, what about these ratios? I saw y plus and back, and I wasn't quite sure what to make of them.
Ah, yes. These are ratios of solutions. Y plus is well behaved inside the circle, while Yers all behaved outside.
Wow.
And these ratios are holomorphic and invertible in their respective regions.
Okay, so different ratios for different regions, each with its own nice properties.
Precisely. And this sets the stage for introducing the Riemann Hilbert problem.
Okay, finally. The Riemann Hilbert problem. What's the deal with that?
Think of it as a way to rephrase these linear q-difference equations. We turn it into a problem of finding a function that jumps in a specific way across a contour in the complex plane. Yeah, like imagine stitching together different pieces of fabric, each with its own pattern.
And how do we define these jumps mathematically?
We use something called a jump matrix, JZ, and it's built using those ratios of solutions we talked about, late plus and J's.
Okay, so the information from the linear system is baked into this jump matrix, which then sets up the Riemann Hilbert problem.
Exactly.
This leads us to the tau function. What is that?
It's a special function, a crucial one, really. It captures the essence of the Riemann Hilbert problem, defined as the Wyndham determinant of the jump matrix, denoted as WJ.
So it's like the unique fingerprint for the Riemann Hilbert problem. But how does it link back to the q-Painlevé equation itself?
It's amazing, really. The tau function is deeply connected to the solutions of the q-Painlevé equation. It's the bridge between the linear world of the Riemann Hilbert problem and the nonlinear world of the q-Painlevé equation.
That's pretty neat. And I noticed the paper shows how this Wyndham determinant can be expressed as a block Fredholm determinant with an integrable kernel.
A crucial step, because Fredholm determinants are well-studied objects, and this opens up new ways to analyze the tau function.
Okay, we've covered a lot. We've seen how the q-Painlevé III₃ equation arises from a linear system, talk about monodromy, q-Bessel functions, the Riemann Hilbert problem, and now the tau function. Where do we go next?
Now that we have this Fredholm determinant representation of the tau function, we can start digging into its combinatorial structure and its connection to other areas like gauge theory. Things are about to get even more interesting.
Can't wait. Combinatorial structure of the tau function, huh? Sounds intriguing. How do we even begin to unpack that?
Well, the paper shows us how to compute the minor expansion of this Fredholm determinant, and that gives us some explicit formulas for the tau function.
Minor expansion. Could you give us a quick reminder what that is again?
Sure. Basically, it's a way to express the determinant of a matrix as a sum over determinants of its smaller submatrices, called minors.
Ah, okay. So we're breaking down this big, complex determinant into smaller, bite-sized pieces.
Exactly. And what's fascinating is that the terms in this minor expansion, they're labeled by these combinatorial objects. Two-component Maya diagrams.
Those were mentioned earlier, right? They're like visual representations of certain partitions.
You got it. Each Maya diagram corresponds to a specific minor in the expansion. And we get a formula for each term.
Okay, so we're seeing this cool interplay between analysis, the Fredholm determinant, and combinatorics with the Maya diagrams.
Absolutely. It's like two sides of the same coin.
Makes you wonder if there are more connections lurking beneath the surface.
Oh, there definitely are. It gets even more interesting because these combinatorial expressions can be simplified and connected to, get this, Nekrasov functions.
Nekrasov functions.
Yeah.
Now, those definitely ring a bell. Weren't those from, like, gauge theory in physics?
Yes, you've got a great memory. They were originally introduced in the context of supersymmetric gauge theories and instanton counting.
Okay, my physics is a bit rusty. Remind me, what are instantons again, and why are they important in gauge theory?
So, instantons, they're these special solutions to the equations of motion in gauge theory.
Special in a way.
They have a non-trivial topology, which makes them stand out.
Topology, huh? So we're talking about the shape, the structure of these solutions.
Precisely.
and they play a crucial role in understanding these things called non-perturbative effects in quantum field theory.
Okay, break that down for me. Non-perturbative effects.
So in quantum field theory, we often use perturbation theory. It relies on small coupling constants.
Right, right. Break down the problem into smaller, easier to handle parts.
Exactly. But there are some effects you just can't capture that way. Those are the non-perturbative effects. Instantons often come into play with these effects, like tunneling phenomena and other quantum stuff that's hidden in the classical theory.
Okay, starting to get the picture. So these Nekrasov functions, they somehow count instanton contributions in gauge theory.
Right. Exactly. They're these partition functions that enumerate instantons with specific properties. And the cool part, they show up in this purely mathematical realm of the q-Painlevé equation.
Hold on. So we've got this bridge between a problem in mathematical physics and this q-deformed Painlevé equation. I wouldn't have guessed that connection.
It's pretty remarkable, isn't it? The paper shows how a theorem by Nakajima and Yoshioka comes into play here.
Okay, what does that theorem do?
It lets them simplify that minor expansion of the Fredholm determinant we were talking about and express it in terms of, you guessed it, Nekrasov functions.
Wow. So we've got combinatorics, analysis, and physics all converging. That's pretty mind-blowing.
It's pretty awesome to see how these seemingly disparate areas intertwine, isn't it?
It is. Now, you mentioned earlier about the paper exploring alternative Fredholm determinant representations. Why would we need more than one?
It's a good question. You might think one is enough, but having multiple representations gives us valuable insights. It's like looking at a sculpture from different angles. Each view reveals something new.
So it's about getting a more complete picture, right? Seeing the whole thing.
Exactly. It deepens our understanding, and also it highlights the underlying structure and symmetries of the theory.
Right, right. It's not just about finding a solution. It's about understanding the deeper connections, like the Becklin transformation. That relates different solutions to the q-Painlevé equation itself.
Absolutely. The fact that these different tau functions, the ones we get from different Fredholm determinants, are related by simple prefactors, it points to a deeper structure, hidden symmetries within the theory.
It's like there's a secret code embedded within these equations, and we're just starting to decipher it.
That's a great way to put it, and it really emphasizes how important it is to explore these alternative representations. It lets us move beyond just solving the equation. We can actually start to unravel the mathematical tapestry that connects these ideas.
So how do these different representations connect back to the q-Painlevé equation itself?
Well, the tau functions, no matter how we represent them, they capture crucial information about the solutions to the q-Painlevé equation.
What kind of information?
Specifically, they tell us about the local asymptotic behavior of the solutions around special points.
So like how the solutions behave near certain critical points in the complex plane.
You got it. By looking at these tau functions, we gain insights into the local behavior of the q-Painlevé equation solutions.
And that local information then feeds into solving the connection problem, right? The one you mentioned before.
Exactly. The connection problem is all about figuring out how to relate solutions in different regions of the parameter space.
So it's like piecing together a global picture from these local snapshots.
Precisely. And the paper shows that solving this connection problem involves a mapping between the monodromy data and the parameters in the tau function.
Okay, so the tau function acts as this bridge between the global behavior, the monodromy data, and the local behavior near these special points.
That's it. A powerful tool for connecting the dots.
Now, you mentioned elliptic gamma functions earlier. Where do those fit into all this?
They pop up in the expression for the connection constant, a key part of solving the connection problem.
Okay, so we've got q-Bessel functions, Nekrasov functions, and now elliptic gamma functions. That's quite a collection of special functions we've encountered.
It might seem like a lot, but each one plays a special role, helping us understand a different facet of this q-Painlevé equation. It's a testament to the interplay between various areas of mathematics.
It's amazing how one equation can lead us down so many different paths, connect so many different ideas.
It really is. And exploring this connection problem and these special functions, it just emphasizes how deep and complex this q-Painlevé equation truly is.
I'm starting to get a sense of that. Now, I can't help but wonder, there was a mention of an algebraic solution in the paper's title. That sounds a little odd, given how we've been talking about these equations as being highly transcendental. What's the story there? An algebraic solution, you say? That does seem a bit counterintuitive considering all the transcendental stuff we've been talking about.
Yeah, it's not your typical algebraic solution. It doesn't capture all the possible solutions, more like a special case.
Ah, so it's a specific solution, but one that might offer some unique insights.
Exactly. Think of it as like a window. Allows us to peek inside the inner workings of the q-Painlevé equation.
I like that. A peek behind the curtain. So how do they construct this algebraic solution?
They start with an ansatz, a kind of educated guess about the form of the solution, and it involves q-Pochhammer symbols.
Ah, those q-deformed factorials. They just keep popping up everywhere.
They're everywhere, and they play a big role here, too. So by carefully selecting the parameters in the ansatz and double-checking, making sure it actually satisfies the q-Painlevé equation, they get an explicit algebraic expression for this particular solution.
So it's like a puzzle, fitting all the pieces together in just the right way.
Exactly. And what's really cool about this algebraic solution is its connection to the monodromy data.
Ah, let's bring that back. How does this algebraic solution relate to the monodromy data? Which, if I remember correctly, describes the global behavior of the solutions.
Right, so the authors show that the monodromy data for this algebraic solution has a very special form. The monodromy matrix, the one that usually describes these complex transformations as we move around a loop in the complex plane, it becomes much simpler. It simplifies to a diagonal matrix.
So the global behavior of this particular solution is much tamer than in the general case.
Exactly. And this special monodromy data translates into specific values for those parameters 0 and se, which we saw before in the tau function.
Right, those parameters that tell us about the behavior of the auxiliary solutions near 0 and infinity.
Exactly. So this algebraic solution gives us a concrete example where we can explicitly link the monodromy data to the parameters in the tau function.
It's like a bridge between the abstract concept of monodromy and the concrete formulas we've been working with.
Exactly. And this connection reveals something really deep about the nature of Painlevé equations and their solution.
Do tell.
We've been saying that general solutions to Painlevé equations are usually transcendental, really tough to express in a closed form. But this special algebraic solution, even though it's not the general case, it offers a glimpse into the structure, the order underlying these seemingly complex equations.
Like finding a rare, perfect crystal. It hints at the intricate processes that formed it.
What a great analogy. It suggests that even though general solutions can seem chaotic and unpredictable, there's this deeper level of mathematical symmetry and elegance at play.
So studying these special solutions, even if they're not the whole picture, can be incredibly valuable.
Absolutely. They offer insights into the mathematical framework that might not be obvious if we only looked at the general transcendental solutions.
Well, this deep dive has been quite a journey. We started with what seemed like a very specific q-deformed Painlevé equation and ended up exploring this whole landscape of interconnected mathematical concepts.
It's been a real adventure. We saw how this q-Painlevé III₃ equation pops up from the compatibility condition of a linear system. Talked about monodromy, how it captures global behavior, and the roles of q-Bessel functions, Nekrasov functions, and even elliptic gamma functions.
And we even stumbled upon this unique algebraic solution, offering a special glimpse into the hidden symmetries and structure of the equation.
It's pretty mind-blowing how a single equation can lead us to such a rich and diverse collection of mathematical tools and concepts.
It really opens your eyes to the beauty and interconnectedness of math.
I hope this has sparked your curiosity, inspired you to keep exploring the fascinating world of q-Painlevé equations. There are so many more mathematical wonders out there waiting to be discovered.
I think it's safe to say our curiosity is definitely piqued. And to our listeners, keep those minds open, keep exploring, and we'll catch you on our next deep dive.